Hello, my name is Ugo, and this is my attempt at doing the U and umpire for the hardest problem I have the solution to, which is trapping rainwater. Um, so first with the inputs and the outputs. The input that we are provided by this is a list of elevations. So we can assume that each elevation is like a block, kind of like in Minecraft or Terraria, where we will have a block of elevation. And in the diagram right here, that shows an example 1, it'll be 0, 1, 2, or 0, 2, 1, 0, 1, 3, 2, 1, 2, 1. There we go. We're provided with that, and with that information, we're supposed to create an output, which is supposed to represent the amount of water that can be contained after raining. The water will be represented by the little blue blocks here. So we have 1, 2, 3, 4, 5, 6. For this list, we would have to output the number 6, and as you can see, that is the case here. So, yeah, that's the problem's description basically. I mean, it's pretty short, as you can see 2 lines right there, given in n non-negative integers representing the elevation of a map. How much water can it trap after raining? In the first example, it's 6. So what we're going to need to do is need to understand what is needed. First, what we need to do is understand what is needed for there to exist water after raining. So as you can see, there has to be some form of containment. Because water is a liquid, we need to contain it in something. So we're going to have a container, and inside of it, we're going to have water. The way we know that we have a container is if there is a left and a right solid, and I guess a bottom one, but the bottom one will likely either be another block or the floor itself, as you can see here. So what we need to do is somehow figure out that we have a left solid block, a right solid block, and that there's a dip in between them for there to be water inside of. Because water would otherwise spill out, or if it was equal, then it would just go across and it wouldn't be contained or trapped in this case, as the problem says. So to start off, we need to have 3 blocks of width first. As you can see, the problem says that that it can be less than 3. I'm pretty sure that's what the constraint n means. Yep. So that means it could be less than 3 because it starts at 1. So what we want to do first is we're going to check if it's less than, if I'm just going to call it in, is less than 3, then we're just going to return 0 because nothing can be trapped without the containment, right? As you can see, because if we just had 1 block, nothing could be trapped there. If we had 2 block, nothing could be trapped there. Even if one of them was off, it would still spill out. And the other way around too. So after doing that little if statement, the little base, I guess, I don't know what it would be called, the precondition, I guess, we move on with the actual algorithm of the problem. Because we need to know that there exists a left and a right block, what we can do is we can have a left a pointer to the left that basically tracks the element at a left spot, and we move it inward towards the middle. And we have another one starting at the right that moves inward towards the left. So the left would start at 0, while the right would start at the length. Sorry, my OneNote is freezing and it does that. I apologize. Of the input, which would be this little, or not, I guess, the list. So the length of the list minus 1, because the length that is provided is the end, or points after it. So yeah. Then what we're gonna need 2 more variables for later on. Just trust me on this for now. We're gonna need an L max and an R max. Or actually, I think I could explain it now. These ones, what they do is they track the height of the pointer's location. So we have, these are like the indices. These are indices. Oops, I forgot the N. Indices. While these two are the actual heights. Because we need to know the height of these two to know whether they can contain something. So we're just going to set these equal to the height at their respective pointers. So because we have the 2 indices already, we can do the input list. Actually, let me change the name of the input list. I'm gonna call it what the problem calls it. The problem calls it height. So we're gonna have height. Height is gonna be equal to this. This is height. So that represents the elevation or the height, I guess, each block. And so we're gonna be getting the height at the left pointer and the height at the right pointer. With this, we can go on to solve the problem. What we need to do is loop through it until all blocks have been covered by the 2 pointers that we have. Since we're moving the left inward and the right inward, but in opposite directions, because they're going to clash in the middle, or well, not in the middle, they don't have to clash there, but they're going to clash eventually going inward towards each other. We will continue going until the left overtakes the right. So what that would mean is that the left goes past it or to the right of the right. And when that happens, that means we've already covered all of the cases. So we're going to do that while the left is less than the right. And all we're going to do is we're going to handle cases where the height at one pointer. Oh, well, first we need to handle the cases where the height at one pointer is greater than the other. So if we have a case where the height at the left, or L max, if L max, or wait, is it L max? Oh, yeah. No. So if the left is less than the right, oops. If the left height is less than the right height, we're gonna want to check it, because imagine we have a case like this where we have this. So we have 1 here, but we have 2 here, and we have a gap here. What we want to check in this case is if we have the left being less than the right, then that means that there exists a spot to the right of the left. This middle can be infinitely, well, not infinitely because the length is limited, but it can be very long. And so long as the left pointer or the height at the left is less than the right, we can check if there exists a dip to the right, immediately to the right of the left. Because if there exists a dip there, like in this case does, then there exists water. Because we can guarantee that because there's something on the left and there is eventually going to be something on the right, there must exist water here. Even if there's a collision somewhere here, we know that if it does or doesn't exist, that we know that regardless of whether it exists or not, eventually it will be trapped by something if there is a dip in the middle, immediately after the left pointer's max or height. So what we're going to do here is we're going to move the left pointer to the right by 1 to check if there is a dip or not, right? So we're going to move it to the right. So by doing that, we would have to add it by 1. Then we're going to want to check or get the maximum height. We're going to want to get the maximum height between the two. So we're going to want to compare this value that we have stored in Lmax and the height at the value immediately after it. And we're going to want to store that value in Lmax. So we're going to get the max of Lmax and of the height of the new left, which is the one immediately after Lmax. And we're going to store that in Lmax. Now, what we're going to do here is we're going to want to modify how much water there is. So water, I forgot to make that variable earlier. We're going to make a water variable. And we're just going to set it to equal to 0 for the start because there's no water yet. Water is going to be equal to the amount of water we currently have, because we're going to be storing it up, storing the number up over time, plus the dip between the first and the second. So okay. So we're going to want to store the dip here. Now, what the max did in the previous statement is it checks, and it gets the greatest of the two values. So if we have a case where, let's see, there's 3 cases. We're going to have one case where there is a dip, one case where they're equal, and the other case where the right one is actually greater than the left one. Right? These are the 3 cases. So 1, 2, and 3. And what the max does is it checks or gets the value that's greatest between the 3 possible options. So if there is a dip, then Lmax will stay the same. If there is no dip, so this is where there's the dip, there's no dip in these 2. No dip. If there is no dip, then what this calculation here will do is it'll add nothing because there cannot be water there if there is no dip. So to do that, we use the pointer that we have at left and subtract it to the current Lmax. Whoops, don't have space. Sorry about that. There we go. So, since we're getting the max of Lmax and height at left, what this does is if the height is equal to or greater than Lmax is before we move forward by 1 to check that if there's a dip. If that height next to the one that we were checking originally is not less than Lmax, then there is no dip. And this subtraction, what it'll do is it'll equal to 0 if height at left is equal to the max, because Lmax becomes that value, and that value minus itself will equal to 0. And that will add nothing to the water that we have. However, if Lmax is greater than height at left, there will exist a dip there, but nothing changes from this operation. Lmax will remain the same, and that difference between the two will be calculated here. So in this case, we have 1 and 0. We can just the max between 1 and 0 will be 1. And then when we subtract 1 by 0, we'll have 1, which means there will be 1 block of water here. And that is guaranteed because we know that Lmax is less than the right max. Because of that, we can guarantee that there will be eventually something to catch the right side of it. And now the pointer will point to the next value because of this. However, we want to handle the other case where Lmax is greater than or equal to Rmax. And this is essentially the same thing, basically, just for the right. So we're just going to be moving right to the left by 1. Rmax is going to be equal to the max between Rmax and the height at the new right pointer, which would be 1 to the left of it. Oh, sorry. Forgot to include the right part. And finally, the little water calculation is the same, just with the right. So water is equal to the amount of water we currently have counted, plus the difference between the R max and the new height that we've seen. If there exists a dip, that value will add to the difference between them will be added as water. Otherwise, nothing will be added. And after that looping is done, we will return the water we have counted. Sorry for the long explanation. It's not that tricky of a problem to encode because it's very, I think it's one of the smallest problems in terms of code length that isn't an easy problem. Yeah, it's pretty short, but the concept of it is a little, well, not a little, it's very tricky, for me at least at first, to find that. But yeah, that's trapping rainwater. This algorithm, if you put it into actual code, should work regardless of, yeah. And basically all we're doing is in this if statement, we are finding out whether there exists a dip or not, because there exists a height to the right. So we get this. We can guarantee that this block exists, and we need to check if these two exist. And the opposite is here, where we know that there exists a block to the left. And we don't really know if there exists a block to the left, but the max statement here will handle whether or not it's flat or not. So we don't have to worry about adding water by accident to the left, because if they're flat, then it's flat. It's not gonna do anything. So yeah. The max is such a key point, and it does so much. It's very difficult to explain, but I hope I did decent at that. Have a good day, and I think that's it. Let me zoom out one last time. There we go. Goodbye.